really getting the opportunity to design something like this is absolutely fantastic, once a lifetime kind of thing, and hopefully people like it enough and get to do another one. So really been wanting to do this since I was about 14, first making amplifiers and making them look like Krells of the day and Levinsons. So really this really kicked off at NAIM just over 10 years ago when we were building ideas, and it wasn't until we reached enough really good ideas that we could really start it. And as Doug said, we wanted to get our manufacturers to come in as well. One of the big ones was our semiconductor manufacturer making transistors for us. I'll tell you about that in a bit. But when you start making something, you know, I say to Paul Stevenson, the boss, I want to make the best amplifier we've ever made. It's a really hard journey to start. What is the best amplifier? You know, is it the most efficient? Is it the smallest, most compact, or is it just good sounding? And ignore the shape. The shape is whatever shape it turns out, like a rocket or a Formula One car. It has to be that shape. So that was the approach we took. It was to engineer an amplifier, and the shape of the physical shape of the power amplifier would define the shape of the product. And what we see now is mono amplifiers with a cut through it where the power supply is. So in the NAIM tradition, we've got the power supply in the bottom and the electronics in the top, but we don't have a big cable going around. The cable would be too big this time. So it's a holistic design, because we don't just look at sort of circuit distortion and frequency response. We look at how the circuits interact with the metal around it, with the sound pressure vibrating it, the way components react to signals as well. So everything has been considered, and we start completely afresh. Quite normally when you're designing a new amplifier, you've got the company standard case and you put a different circuit in it, and so there's a lot of givens, and it's quite easy to come up with a new design. But when you can do any shape, you as a designer, you're doing notes and sketches for a long time until you feel comfortable, and then you build lots of prototypes. And another really important point is designing from the beginning to be an ultra amplifier. I think like cars, if you like take a Golf, Volkswagen Golf, and they can make it into a GTI, but a lot of the stuff is still a family car underneath, so all the stresses and the quality in the suspension bits, is that good enough to go with the car? And the same with amplifiers. If you just change the transformer and make it higher rails as everything else, is it all the same quality? So that starting point is really important. And yes, so the end result is a real mix of engineering, science, art, but really just going to crazy details. Okay. That in the corner, sorry. Can I go back here? Yeah. That was one of the original sketches from years ago of how it should look, and some circuit notes.
May I have, when did you start building this? Or designing it?
Designing it, I think first, the original sketches of that circuit was probably about 25 years ago, coming up with ideas for it. But it really started taking shape 10, 12 years ago, something like that, when I joined NAIM Audio.
Thank you.
That was a real opportunity, working at companies like Cambridge Audio, NAD, Roxanne, Quad. You couldn't do it there. It just, you know, it would be a little bit more expensive than the other stuff.
Yeah.
But Paul Stevenson said, it doesn't matter what it costs. And you think, does he mean it? And I remember one day I said to Paul, I said, we've got a really great idea for this new transistor, but it's going to cost, each transistor is going to cost £50, and we're going to use 36 of them. Is that okay? And it's just, don't mention cost ever again. So. But still, as an engineer, you like honesty in your design, and so I'm not going to gold plate things, cover them in diamonds and things like that. If it doesn't add to the performance, then it still didn't get in. So it's still quite strict. So we did use diamond in it. There are diamonds in it, but diamonds conduct heat really well, and so we use a diamond thermal paste to bond the transistors down, and it's really quite cheap. It's an industrial design, 10 to the minus 15 meters across, but it's it's about 9 times better than normal thermal grease. So and it still only costs €10 per product to put that in. You use it in a computer.
Yeah.
So design goals for the NAC S1, the NAIM Audio Control Amplifier, Step 1. So design an ultra analog preamp, so not digital. We can add digital to it as another product at any time. So we want to get analog and make it really pure. When you're reviewing equipment, it always sounds better with one source connected rather than two, and so we want to eliminate that. We want to make the volume control we've always favoured motorised pots. They're simple, they sound good, but in terms of app control, they're useless really. And the 2 channels, one gets louder before the other, those kind of things. So we want to get rid of that. We want to give flexibility with different types of inputs. As balanced, we've got DIN as well, RCAs. Mechanical isolation, NAIM's done that a lot. In the CD555, all the circuit boards are on suspension, so we carry those through. And electromagnetic isolation as well, so screening where it's appropriate. So there's a few approaches you can do on circuits. You can design really simple circuits that have distortions, or you can design circuits which are more complex and are absolutely pure. But if you take a pragmatic approach and think about it sensibly, and how instruments and voices work, then it's really not worth getting to 5 noughts distortion. So we take the approach of using a simple circuit which doesn't exhibit any sort of distortions or noises that wouldn't naturally occur, so sounds that are pleasant for our ears. And then we make them better by putting them in a really nice environment. So a simple circuit, remove vibration from it, put really clean power supplies on it, and just take care of it. And we find that sounds good. Also, like many other companies, match the components. It makes a lot of sense. We also find the through-hole components are sounding better than SMD. I think there's a few different effects here. The most dominant one is the flexing of circuit boards, which stretch components, and they're on ceramics, and it changes their properties. You see on a capacitor, as you move the plates, it squeezes the volts out as you squeeze the plates in. So through-hole components, the legs bend and the components stay still. It's getting harder to do that these days. There's On Semiconductor have just said no more transistors through-hole now. In their small ones, that's it.
The small ones, yeah.
Yeah,
they still have the big ones.
Yeah, still got the big ones, yeah, the big output transistors they've got. Everything else, gone. Same with capacitors now. AVX, they've just killed off a whole load, so it's getting hard. We get some custom ones done to get around it. And we developed the DR power supply. So this was one of our core bits of technology we had to get right before starting the project. DR stands for discrete regulator. So I'll tell you briefly what it is. We start with a buried Zener reference. So it's like a Zener diode, but it's got a passivation above the silicon, which stops impurities, so it's really low noise. And then we use an NAIM amplifier to boost that up. So that starts at 7 volts, and if we want to get 35 volts, multiply it by 5. And then we use that output to power the Zener, so it's bootstrapped. So the quiet voltage powers the quiet Zener, and it works really nice.
You use adjustable SIM diode?
No, I don't
like
actually.
TL431?
TL431's really nice. A band gap reference. It's very quiet.
You have a better one.
Yeah, LM329.
Okay.
It's lower noise, but also there's another complication because there's some really good adjustable ones. TL431s are great. I've used it lots of times, but it's harder to do positive and negative supplies symmetrically. Yeah.
Yeah, I know.
So with a Zener, you just turn it over, and so we can make our positive and negative supplies identical, so the response is good. So single source. So this is really quite easy concept to do. You just have more switching relays. So you switch the ground and the signal. So it's only one input selected, and we can say that the stream is connected to the DIN socket or the RCA, and the dealer can adjust that for the customer. So we could ultimately do custom laser engravings, and so they could have their children's names on there if they wanted and select it. And the single source sounds different because of, I mean, you guys will know, it's sort of conducted radio frequency interference down the mains. You also get effectively like loops, so like aerials going around capacitively coupled through transformers. So we do it with the read relays. So the read relays are nice because they're encapsulated, so the contacts work really good. They're very good for small signals, whereas the other ones you've got to put current through the contacts to make the contacts work, and reads work nice. But you've got to be careful with them because they've got a coil wrapped around, and so you can capacitively couple your coil to the signal. So you do have to take some care and make it very quiet, otherwise it's like a little transformer as well, a sort of 3,000 to 1 turns ratio. But do that and it's all good. Volume control. Hi-fi designers spend so long trying to do volume controls, and it's so many things they have to try and do. So first of all, you want to try and make the sound pure. Then you want to get a big range. You want to get the channel balance absolutely perfect. Frequency response gets overlooked quite a bit. So with a normal potential divider, if you're at the top, the output impedance is 0, so the signal comes out faster. And if it's at half volume, minus 6 dB, then if it's a 20k part, you get a quarter of that as 5k. So your frequency response comes in a little bit. So again, you want to eliminate that in the design. You want it smooth, so as you adjust it, you don't hear the zipper noise. And you want it absolute volume, so we can say go to minus 10 dB, so that tablet volume controls work. And input trim level, so all the different inputs, if you've got a phono stage, it needs boosting or taking down. So the way we've done it, we tried to make one volume control do it, and we couldn't design it to meet all what we wanted it to do. So we've used 2 volume controls. The first one is a resistor ladder. And instead of an R to R ladder, do you know how an R to R works? Mm-hmm. You do combinations of digits, and it switches in various resistors. So at one volume you might have 1 switch on, at another volume you might have 3 on, so the sound varies. With a straight ladder, it's only ever 1 relay, so we do that. It's a very pure way of doing it. And we do combinations of fine and a coarse, but that would have zipper noise. So we've got a second volume control in there, and as soon as I touch it, we switch in another volume controller chip, and it goes to that one. So that looks at the 0 crossing and chooses the volume. Then when you let go, about a thousandth of a second later, the read relays will switch back, and you get the volume control. We've also arranged for the circuit to have the same input impedance and output impedance, so the response doesn't vary at all levels. And so we can tune the circuits, and that stays at all levels. So that's the volume control. It was a lot of fun designing that. It's one of those ideas you write out every year when you have a big meeting when we discuss tech, and it never gets done for years, and it eventually gets designed. So isolation, very big on NAIM. We do all the circuit boards mounted on brass. Again, important for the read relays, which have got magnetic fields, so if they vibrate. The transformer, if you use a toroid transformer, the transformer grows and shrinks with magnetics. Magnetostriction, it's called. Mm-hmm. So when you imagine it's doing that, the center point is fixed and doesn't move. So normally they're bolted down to a chassis, and the transformer's doing this, and it's bending the chassis. So we mount it on A-frames, and the transformer's there, and the bolt through it. So it can move. And optical isolation from the controls. It's an obvious thing to do. Eddy current isolation as well. So eddy currents, I don't have a magnet with me today, but if I was to drop a magnet down this heatsink, it would fall very fast and then hit this and go very slow, and then fast and then slow. So what that would be doing is inducing a current in the metal which produces an opposing magnetic field and holds the magnet out. Heinrich Lenz did it first, 1935. So this separation here prevents any magnetic currents from the transformer in the bottom getting up to the top. So system flexibility we've spoken about before. You can adjust the input sensitivity, assign the names. That's the sockets we've got. I'll show you the back panel in a second. And you can control it. Infrared remotes, the NAIM app, when we've got a control cable in the back from an NDS. And we've got 12-volt triggers for legacy systems. Okay, so here's the rear. So all the inputs up here, outputs here. These outputs are the same height as the inputs on the power amp, so it's nice, neat, tidy wiring.
Those RJ45, it's only for control?
Yeah, it is, yeah. So we use what's called a CAN bus, control area network. We use it in the Bentley. And then that communicates between the preamp and the power amps and anything else we want to put on that network. It does really basic stuff, like controlling lights, synchronizing powering on and off.
There's a very smart way.
Yeah, it's a very robust way of doing it. Yeah, and the USB is for updating software, so it's not got a DAC in there. Okay, so the design goal of the power amp, we wanted to make something that drove big speakers in big rooms, not run out of any power. So we wanted to have at least twice the headroom of what we'd previously done. That was 140 watts and that 500. So that came around about sort of 600, 700 watts. And if you look at the voltage of transistors and currents, we knew we could take it to 1 horsepower, 746. And I quite like engineers and what they've done, so James Watt and all those people, sort of a bit of inspiration. So that set the power. And we wanted to be really pure as well. We didn't want it to add a coloration to the sound. And be incredibly fast. Normally when you make a bigger amplifier, it gets slower. So we had to come up with a new way of doing that. Electromagnetic isolation, even more important in this because of the really strong currents. So we came up with a new amplifier approach, and this was zero global feedback. So we've got a pre-amplifier section at the top, which is 30 dB gain, and then the high current stage here and the power supply at the bottom. So the power comes up and the signal comes down, they meet, and then the speakers go out this way. And this, we eliminate magnetic interference by keeping loop areas small. So we've made our own transistors. These, we match the die. So when we get the silicon die, it's chopped up and we serial number the die. So we know that the silicon on adjacent die is going to have similar properties in gain and response. So it's a really great way of making essentially one big transistor, but it's in separate packets. And they're all serial numbered, and we've got all the parameters for them. So the result is that we can get over 100 amps drive and 9 kilowatt bursts. And it's a lot of power.
You can weld with it.
Yeah, you can.
Yeah, yeah. Had some fun in the lab with that. Yeah, I can melt solder very fast with it.
You can make a screwdriver glow.
Yeah, yeah. It takes chunks because you test protection circuits, and you do it in controlled ways. You do bursts, and you go, yeah, tried 1 ohm at all levels and things, and then you do what you really want to do and put pliers and screwdrivers on it. At different frequencies. Yeah. So some of the same isolation techniques in the preamp we do in the paramp as well. The one sort of difference really is the way that we've split the design, so we've got the delicate stages isolated away. Now with ceramic insulators as well, it's not really relevant to the preamp. This is where we built the power transistors down to the chassis, because I'm sure you'll know the collector is capacitively coupled to the chassis, and the chassis is connected to earth, and if you separate it by 3 millimeters, the capacitance drops enormously. So we use a ceramic insulator, which works even better than traditional mica washers. Rear panel, very nice and simple. Only one input, only one output. The input stage is a true instrumentation amp, so you can feed an unbalanced signal into the balanced input, and it works itself out. It's a bridged output, so it's balanced all the way through the power amp. So it's very quiet, turning on and off. We tested the soft start because it's such a big transformer. Tested that 40 times. Tested the volume control a couple of million times, and we can do custom finishes for customers. Yeah, and that's it.